In real analysis, compactness operates as the geometric boundary between the finite and the infinite. It is the property that allows us to treat infinite collections of points as if they were manageable, finite objects. Many students first encounter the sequential definition. This rule dictates that a set is compact if it forces any sequence constructed within it to cluster. The sequence must yield at least one accumulation point, and that point must lie strictly inside the set itself. But the topological definition takes a different approach. As illustrated in this model, a set is compact if every open cover of that set admits a finite subcover. An open cover is simply a collection of open sets whose union contains the entire target set. That initial collection of open sets can be uncountably infinite. The ability to extract a finite number of those sets while still covering the target provides a functional reduction in the set's complexity. The question is how an abstract topological property, collapsing infinite covers down to finite ones, translates to the physical geometry of the real number line. The Heine-Borel Theorem provides the exact translation. It states that a subset of the real numbers is compact if and only if it is closed and bounded. The theorem is named for Eduard Heine and Emil Borel, whose work helped bridge the emerging field of point set topology with traditional real analysis. This equivalence serves as a functional tool. It allows us to substitute the abstract topological definition of compactness with geometric properties like distance and bounds. To use this theorem rigorously, we cannot simply memorize the rule. We have to mechanically derive the geometric limits of boundedness and closeness directly from the topological premise. We will start by proving the forward direction. Assume we have a topologically compact set K. Our objective is to prove that this topological property forces K to be a bounded set. We begin by constructing a highly specific open cover. For every single point x within K, we defined an open interval with a radius of exactly 1, centered directly on that point. Because we anchored an interval onto every single point, the union covers K entirely. Now applying our premise. Since K is compact, this infinitely dense mesh must contain a finite subcover. We are left with a countable number of intervals. Taking the union of a finite number of bounded intervals results in a bounded set. You cannot reach infinity by adding a finite series of finite distances. We can explicitly calculate the absolute bounds of this new overarching set. The lower bound is the minimum of our finite interval centers minus 1, and the upper bound is the maximum of those centers plus 1. Our compact set K is trapped inside this finite outer boundary. Therefore, the property of compactness inherently forces boundedness. Next, we must prove K is a closed set. We will do this via contradiction. We assume there is a point y that acts as a limit point for K, but exists outside the boundary of K. To test this, we construct a new topological open cover. For the radius of these new intervals, we calculate the geometric distance between each point x and our external limit point y, and cut it exactly in half. We invoke compactness again. This infinite collection reduces to a finite subcover. Because it's finite, we can survey the edges and find the one closest to y. This definitive minimum distance between the boundary and y is called epsilon. Here lies the contradiction. This epsilon gap acts as an impassable barrier. It is mathematically impossible for any sequence originating entirely inside K to cross that gap and converge to y. Since no sequence in K can reach it, y cannot be a limit point. Our initial assumption fails. A compact set K cannot possess external limit points. It contains all its limit points, making it closed. We pivot now to the reverse direction. We assume a set is closed and bounded, and we must prove it guarantees a finite subcover. We start with the simplest case, a standard closed interval from A to B. Assume we lay down an arbitrary open cover across this entire interval. We define a subset S, consisting of all points x between A and B, where the segment from A to x possesses a finite subcover. Because S is bounded by B, it has a supremum. We mark this as S. The critical logical test is this. Does our supremum S equal the final endpoint B? Assume S is strictly less than B. Being inside our closed interval, S must be covered by an open set from our original cover. This open set extends slightly past S. reaching a new point, S plus epsilon. This breaks our definition of S. If the subcover reaches S plus epsilon, then S was not the absolute upper bound to begin with. The only logical resolution to this contradiction is that the supreme on S equals B. The property extends all the way to the end, meaning the entire closed interval from A to B guarantees a finite subcover. We expand this logic to finish the proof. If we have any arbitrary closed and bounded set K, its bounded nature means we can place it completely inside a larger closed interval from A to B. Because K is closed, the space outside of it, its complement, is open. We can use that single open complement to fill in the gaps and finish covering the larger interval. We've established that the full interval guarantees a finite subcover. If we extract the finite sets covering the interval and remove the complement, the target set K is forced to have a finite subcover as well. The Heine-Borel equivalence is verified. In the realm of real numbers, being topologically compact is synonymous with being closed and bounded. While this equivalence is a useful tool, the open cover definition remains the universal standard in advanced mathematics. Relying on closed and bounded metrics can lead to errors in abstract non-Euclidean spaces where distance behaves differently. Understanding the Heine-Borel theorem requires recognizing the mechanics beneath it. By preventing infinite escape through boundaries and capturing all destinations through closeness, we mathematically guarantee that an infinite space can be fully tamed by finite information.